work with Linux. And I think this year, right, Matheus, you start using nuttx.
I have unfortunately this project was discontinued, right? It's the Beagle 5 board, the RISC-V processor Beagle board, and I had a port for RISC-V 64-bit 4th nano framework running on this. The .NET Core don't has a port for RISC-V yet, so are the first bits of .NET running RISC-V. So I have it here. I call it .NET. I can set a help here. Oh, and this. No problem. I want to show you guys that I'm running here my part of the .NET Nano framework. This fault is because I'm not handling because I need to pass here a folder with this folder. You can see has the assemblies that I said, the portable executables assemblies. So the .NET Nano CLR implementation load these assemblies and print or execute the code, right? Interpret the bytecode from the assemblies compiled from C# code and run natively on the system. So this is the port for the Linux RISC-V running on the Beagle 5. It's a Visual Studio C++ solution that has their respective .vcx. Where is the file? Here, the Nano CLR VCX project. So the Visual Studio C and C++ project use this file. It is an XML file, but it's kind of, let's say, the make file of Visual Studio C and C++ project. Has all the filters to define switches to here, for example, to switch features inside the code, filters to link to includes, also to call the source code files and everything. So I get this file and make the CMake list file of this to use it on CMake. Okay, so it was the easy part, right? The hard time that I get it was trying to pass the Windows 32 API to POSIX. But I will talk firstly about the .NET Nano framework, a bit about the history of the .NET Nano framework. I will talk a bit about the Linux port, and after that, the nuttx port, and at the end, some demos. And a spoiler here, I think it's the first time that I will show some .NET code running on RISC-V architecture. At least publicly, it will be the first time. So at the end of the presentation, we will have these demonstrations. Also, I have to leave some disclaimers here. All the stuff that I will show today is work in progress, right? And I'm not being funded from any group or institution to do this. I'm doing this work in my spare time. So it's I think it's good to make it clear that is some work in progress, and it would be good also to show you guys to receive feedback, right? So let's go started talking about the .NET Nano framework. I don't know if you guys already know the .NET Nano framework, but the goal of the .NET Nano framework is have implementation of the common language runtime. Since then, the first release of the .NET micro framework was in 2015, and you can see that we had it's a copy of the slide of .NET Nano framework, right? They has the same features, but was discontinued, or the project on GitHub has this last release in 2050, and Microsoft don't care about more the .NET micro framework in this year, and the contributors that are funded to work on this project also leave the project. And at the time in 2016, some other contributors of the project, when Microsoft opened this, some contributors make a fork and try a spin-off to the project, right? So José Simões from Portugal make this spin-off of the .NET micro framework that is called today .NET Nano framework. This has a new license, it's the MIT license, and they are maintaining together with the community. Today, it's all drove by the community. We have a lot of other RTOS targets that us also have maintained by the community. Also, I put here the Linux and nuttx in head because it's not official yet. I'm working to also mainly upstream these ports, these targets to the .NANO framework. Also, at the time, we have other forks, for example, the tiny CLR operation system, but this is specific for the hardware from the GHI Electronics. They have some computer modules and microcontrollers on modules, and they maintain this tiny CLR OS that is also a spin-off, also a fork from the .NET micro framework, but unfortunately this is proprietary, and it only supports the GHI hardware, right? This is the diagram block. As I said, we have the Microsoft Core lib, the subset of the Microsoft Core lib that has the system name 5, for example, the 64 architecture. I have to make some changes. I hope to, after that, port it to nuttx. So I choose the Windows 32 target repository of .NET Nano framework. This is so this is the root of the .NET Nano framework repository. You can see that we have two folders here, the targets and the targets community. Mainly the targets community are targets that are drove by community, and it is community that maintains these targets. And inside the repository, the mainstream, the main line, we have these targets, and we have the Windows 32 target here, and you can see that is a .NET is a Visual Studio C++ solution that has their respective .vcx. Where is the file? Here, the Nano CLR VCX project. So the Visual Studio C and C++ project use this file. It is an XML file, but it's kind of, let's say, the make file of Visual Studio C and C++ project. Has all the filters to define switches to here, for example, to switch features inside the code, filters to link the includes, also to call the source code files and everything. So I get this file and make the CMake list file of this to use it on CMake. Okay, so it was the easy part, right? The hard time that I get it was trying to pass the Windows 32 API to POSIX. But with this done, I had the Linux port running. I have some, let me connect here. I have this one. Yes. So I have one. Yeah, this is let me show here on my desk. Yeah, here. It's a shame that the project was discontinued, right? Okay, let me back to the presentation. It was very, very straightforward. I had to change, let's say, on the codes, on the system codes, I don't have to change anything. I had to make some small changes per platform. For example, I can show here on my nuttx repository my git log by author. One of the things that I'm stuck with about these instructions that Rodrigo helped me on the email list about this. So I get the same implementation from the ESP32C3 to fix this. Also, what more I got? Oh, also I had as C++ application, right? I'm using the lib LLVM libc++ implementation. That is cool. And yeah, I think. Oh yeah, and I had a little problem using the uname. Yeah. For example, here on Linux, I have this on the platform abstraction layer that is a call to the system namespace, system info, on string property. So this on Linux and nuttx, I'm doing a call to the uname to get this information at runtime about the boards that I'm running, right? So this needs the struct UTS name that is implemented also in nuttx, but what I was trying is put a define here for Linux and nuttx. The problem is that on the nuttx we don't handle the case of the mangling as I'm using the C++, right? So for the nuttx case, I had to put this extern C here because when I was building this, the compiler was alerting me or writing me error, outputting an error that the uname was not exist, right? Yeah, and I think it's only these challenges that I got trying to, and also to make file, right? At the time, I don't check the use of the same make list, but this is some work that I had to check to use the same make list, to try to use the same make list also for the nuttx. I see that is possible, but at the time I think it was more easy. Oh, where is my application repository? Let me open the application repository. Where is samples? Oh, let me. So at the time, I thought that it was more easy port the CMake list or convert the CMake list to make file following the examples of other applications that we have on the applications repository. So with this, we had also the nuttx, the .NET Nano framework running on nuttx, right? So it's demo time. Let's run some C# code on the nuttx. Where is here? My samples. Let me open here a sample. Let me open here the C# hello world. Here I am on Linux, right? My samples here, I try to use only Linux, right? To not be tied to the Visual Studio. Okay. So I have this here. I will rewrite this, right? Let's write from scratch this guy here. So you can see it's a basic .NET project. You can see the solution. You can see the CS proj, the program CS using the namespace, the public class, and the public static void main that will execute our application. So let's begin. No, we don't have console here, right? Someone wants to talk something? Nope.
No, that was just because your internet went a little bit bad and it was not showing your screen. It happened again, and it's the most important part. So.
Oh boy! And now it's okay.
No, it's still not okay.
I am seeing normally here, Sarah. Maybe it's your internet.
Oh, for you it's working now.
Yes, I am following all the editing you are doing in your VS Code file in your file in VS Code. Yes.
Okay.
Okay, go ahead.
Probably we can see too, so it's okay.
Okay, so I'm continue here. So as you can see here, I'm using the system namespace, right? So this system namespace are implemented in Microsoft Core Lib, the subset of the Microsoft Core Lib. In the system console, we don't have it because the implementation of .NET Nano framework, they implemented the diagnostics in namespace. So here, if I want to show something on my serial port on the nuttx, I had to use the diagnostics right. Yeah. Wait, I forget how to do it. Let me. Is the bug? The debug is inside this namespace, system.diagnostics debug, right? So you have this write line and writes and everything inside it. So let's debug here. Write line. Let me type a hello world nuttx. And let's use here variable inside here. I want to print the system info on string. This is good. This is cool because I can show you guys how it is implemented inside the Nano framework platform orchestration layer. So you can see that here I have this system info namespace, and you can see that is from the Nano framework runtime native namespace. So these are implemented inside the Nano cellular. Okay. So when I call this will call the implementation here on the application side that I show you guys here. The Nano framework runtime native system info always string. So this will call for us the uname and will fill the uname data for us, and you show at the runtime the information from the board. Okay. Also, another cool thing that we have on .NET Nano Framework is the threads. We have only one thread running, the main application, but they also use time slices to use threads, right? So I can easily type thread here and put some lambda function inside this thread. For example, forever loop here. Oops. And let's put some counter. Put this counter here. Okay. And I always forget to make the start of the thread. Okay, so now this thread will start. So it's easy. I have a new thread here. So also I will put a while here. While true. Let's put this counter to be outputted to us. And for each of this, I want to sleep on the main thread. Where is my sleep? I'm not seeing. Here. For 1 second. Oh, no. 500 milliseconds. Okay. So it's done. As I'm running here on Visual Studio Code, this is not integrated to the IDE, right? So it's cool that I can show you guys the internals of everything, but on Visual Studio, you have this all integrated, the build system, the debugger, the flash, and everything. Today on nuttx, we don't have this implemented, this wire protocol, right? Is work in progress also. I have the tasks in, VS Code has this cool tasks JSON that you can write tasks to run it, and I write everything here, but I will run on the terminal because it's cool to show the internals, right? So what the Nano framework use is the Microsoft build Roslyn. So this gets the solution and compiles as a default .NET application. You can see if I list here my /bin debug in the folder here, you can see that we have the executable, the C#.NET executable, right? But also you can see that we have the portable executables. As I said, on running on Linux, these portable executables are the shrunk version of the assemblies ready to be run on the Nano CLR, right? So these guys that I need, and remember that I talk about the C# projects, the C# templates that Nano Framework implements. You can see here that I put some verbosity on the output, so you can see the steps. In one of these steps is Nano generate binary output. This step is a custom step by Nano Framework that generates the portable executables that you use. So you run this on the ESP32C3. I have it here on my desk. Yeah, it's here, right? So let's try run this on this guy, right? So to make it more easy, as I'm using the ROM-FS implementation from nuttx. So I'm getting the portable executables and putting in the ROM-FS example, and I mount this ROM-FS, and point the .NET Nano framework application to this folder to run, to read this portable executables and run our application. But also, I have here some implementations in a Docker container. Because in a Docker container, I already have the nuttx pre-compiled, right? What I'm doing here is share my folder /bin/debug. So I have a script inside this container that copy every portable executable for this /nef folder here. So I can create a binary for ESP32C3 with the application, right? So let's run it. As you can see, the nuttx is already configured and pre-compiled. It is rebuilding, let's say, the runfs header with my application. And it, at the end, will generate in the bin/debug the .nef.bin file that I can flash on my ESP32C3. Okay, yeah, it's here. So I think I don't make a cleanup on the bin debug. So you can see that I have also the UF2 file that I'm using on the Raspberry Pi Pico, right? But let's use first this one here, generated for the ESP32C3. First, let me copy this from here, .NET bin to, I have a folder with scripts to flash here. So I have a script here to, let me put this in boot mode. Oh, I have to pass here the USB 0. Okay, and flashing. The board is here flashing. Let me see if I can put it a bit small here. Okay, I will click it. I want to run it together in the screen. My computer is beginning to. Okay, it's good. So we have the board flashed with my nuttx generated with my application. So I can now connect to serial of board. Okay, so we have here my nuttx version with .NET application. Yeah. So you can see that's running on ESP32C3 dev kit. But first, you can see that we don't have the /nf or any of the portable executables here. So I need first to mount the runfs. For Raspberry Pi, I already make it all automatically, right? We have a startup script to mount the runfs and call to .NET directly. But for the ESP32, I make this way to show step by step. I think it's cool to show the internals here on the workshop, right? So after that, I have my /nf with my portable executables here. So let's remembering what we are expecting to have. Output with the hello world nuttx, information about the board, right? The uname information about the board, and or counter that is incrementing inside the thread, right? Let's see if this will happen. Live code is a mess. Let's see if this will happen. And not work it. Oh God. Something don't work it. It's always live code is always
some live demo that work from the first time should be exception. So it's not
yeah, you can see that it's not working. It's being stuck also on the thread. I don't know. So but
at least the first time it run.
Yeah, at least this. Okay, but let's try another example. So let's see if we have more lucky.
Do you have some idea why the thread is not running? Because you said I always forget the start, but you put the start there.
This time I put the start here. Yeah. So I really don't know what I'm doing wrong here.
That happens. Happens normal.
But okay, let me open another one here. I have the blink. So this is cool because it uses the peripherals. I have time yet? Yeah.
Yeah, enough.
So let's open this one. Okay, so this is using our system device GPIO here that I talk about, the .NET IoT from Microsoft. So on this demo, what I'm doing more or less the same thing, but I think I not have the threads. Yeah, I only have a while true, right? And here I'm running for each of the platforms, target platforms that I already worked. And here on the SP32C3, this you try to access the ping. Let me see here if this is connected correctly. The ping 8, but this is on the ping 7 here on my connection. So let's change this. This is the chance of this work is being small. Okay, so I change here the LED pin number, and you can see here the GPIO controller that is from the system device GPIO, right? I have a new GPIO controller here, and inside the GPIO controller object, I have this calls to open pin, to write value, to read value from the GPIO controller. So I'm using it to make a blink here on the pin number 7 of our ESP32 C3s. Let me check again if this is correct. Yeah, it's the 7. Okay. So let me build this. Okay, calling the Microsoft build. As Microsoft build, you build the .NET application, you call the Nano framework steps, and you create for us the portable executables. I will call again my Docker image to create the binary, and it will update the ROMFS header, and you create for us the binary application. Okay. Okay, compiling. Staging. Let's see if we have more luck now. I tried this demo sometimes, and in live, it's not working. Cool. Okay, so I have it. Let me copy to my. Yeah, this one. Let me copy to my. Yeah, here, and let's flash it. Okay, I'm on the right one. Let me put it in boot mode and flash it. Okay, so let's access the nuttx shell. It's here. Some spoiler that I can show. I don't know if I have the time to go deeply on this, but here on the GPIO, I made some changes to use some structs to send the pin number at runtime. So, for example, let's test here if my LED is connected on the port 7 on GPIO 7. So I can pass here to GPIO pin 7 output 1 to the dev. I think I have to show this. We don't. I have the GPIO out, the GP out in GP out 0 in 1, but also I have this GPIO 0 that has this, let's say, generic GPIO lib implementation. So I can call GPIO pin 7 output 1 to the dev GPIO 0. And the LED was turned on. So yeah, it's connected to the right pin, right? Let's see if this will work. Oh, I have to mount the /nf. Okay. Oh, it is working. Thanks God. Thank you gods of demos. So we have here the LED blinking on the port 7, and also the output of our code. So it's doing what we are expecting. Where is the code? Here. Yeah. So blinking side while and the GPIO controller open. Yeah. Okay. So work in progress, right? As I said, this is a work in progress. I have the GPIO implementation today, only as a proof of concept, right? That is working. That
I think about 2 years ago, Greg was so kind to do the initial port for that part. Since then, we have worked hard to improve support, and we've learned a lot. And now we're working on getting the new part ported to nuttx as well. So I will be doing this together with my colleague, Peter. He's here as well. So let's see if it will go to the next slide. So we're both working for NXP Semiconductors in Eindhoven, the Netherlands. We're part of the Automotive System Innovations Group. And we're working in the mobile robotics team. That's an international team between many business lines as well. We have people from the Netherlands, where we are from. We have people from Germany, France, even the United States and Canada. So we're a very international team. And yeah, we are working on enabling NXP technology for autonomous drones as well as for rovers. And we're creating reference designs and development platforms so other companies hopefully get inspired and start using our products in their systems. So some things we have done in the past are vehicle management units, as well as CAN and Ethernet hubs, which is also topic of today, part of it. and battery management systems, which we already discussed yesterday. And most of these systems also run nuttx because it provides a very nice platform for us to develop applications on. Some other things we do are the organization and support of hover games and NXP Cup, which are both competitions. Hover games is for professionals, students, and enthusiasts to work on autonomous drones. And NXP Cup is for students to work on autonomous driving with small RC cars. So these are the actual topics we will be discussing today. The first part will be about the actual main reason why we are bringing nuttx to S32K3, and that's a small CAN-hub board that we are working on, which has the S32K3 microcontroller on it. I will do that part, and after that Peter will take over and he will discuss the S32K3 chip itself, as well as our work on porting nuttx to this chip. And he will also explain some of the functional safety features, which is the main topic for this particular chip. So let's first get to the main reason why we are actually working on nuttx for S32K3. That's this MR CAN-hub K3, which stands for Mobile Robotics CAN-hub with an S32K3. And it's a new board that we are currently designing. It features the new S32K344, which is a lockstep M7 core. Peter will come back to that later. It's a very nice small board that we are designing. It's about 8 by 6 centimeters, so I think that's a little bit bigger than a credit card. As the title already says, it's a CAN-hub. It features 6 CAN transceivers, so that's quite a lot, as well as a 2-wire 100-base T1 Ethernet transceiver. So the main purpose for this board is the CAN-hub functionality, but it will also function as a first development platform for a future vehicle management unit, which we might want to develop with this chip. So it also has all the functionality that you may want for that, including UARTs, I2C, SPI, even an IMU connector to connect an external IMU to actually get all the functionality there. The nice part about it is that will also be able to take advantage of the safety features that are part of this S32K3 microcontroller. A third purpose of this board will be some motor control exploration, where our idea is to have motor control running on one core that's without nuttx then, so bare metal motor control application. And on the other core, we could run nuttx and also use UAV CAN, which runs on top of the socket CAN implementation that Peter nicely presented last year. So that we can still take advantage of all the features that nuttx has. So in the picture on the right, you see a first impression of what the board might look like. There's plenty of connectors and I/O on there, so it should be a very nice development board. So this is a current vision of how the mobile robotics ecosystem we would like to have it look like. So the core of this, I would like to say, is the vehicle management unit. I'm not sure if my pointer is visible. Probably is not shown, but it's shown on the left. One of the blue, yeah, there's many blue boxes on there. But that's the main part of most drones and rovers. That's the part that controls yeah, how the vehicle steers in real time. So what we envision is that this will be connected to the CAN bus, and then there will be many peripherals and controllers that also hook up to this CAN bus. Traditionally, this used to be a bit more basic with just pulse width modulated signals, just wires going directly from the vehicle management unit to a motor controller. But we would like to centralize this into a few CAN buses. So the part where this CAN hub comes in is within the bus itself. So that's the orange part. And in particular, also, it will help to connect peripherals to the CAN bus, because it also has some UART and SPI functionality, so it in part can also play the role of a CAN node. And because it has Ethernet, it can also provide a connection between the CAN buses and the Ethernet that might be on the drone or rover. So that's the primary application that we already discussed, and there's also the two secondary applications. There's the vehicle management unit we would like to also build on top of this board, as well as the motor control. Here we have a block diagram of the CAN hub. So in the center we have the K344, the main microcontroller, and there's plenty of I/O, as I've already mentioned. The 6 CAN transceivers, which there's 2 of each. There's these are some of the latest and greatest CAN PHYs that NXP has to offer. There's an FS26 PMIC on there for the power management. There's even a secure element for authentication, quad SPI, memory, and yeah, as I mentioned, the automotive Ethernet. So yeah, we're currently still very busy working on this board. The timeline is that we're planning to have hardware very soon. The board is not even there yet, although we are already working on software. So we are in the final stages of layouting. So you see a picture on the right that was from maybe 2 weeks ago, I think. We're almost there now. So hopefully the board will be there for our internal purposes in about a month, maybe 2. So that's Q3 2021 still. Our other target for the software is that will be done also this year. We set that target at Q4, but in fact we're already in somewhat of a workable state. We already have nuttx booting, we have some peripherals going, so that's already very nice. So after that, we hope to be able to release the hardware as well as the software in early 2022, but that's still to be determined, also because we're working with some bleeding edge chips that are still in pre-production, only available to some customers yet. So we hope when that becomes publicly available, we will also be able to release the board. That also means that we will release the design files. So you will be able to check the actual schematics and layout and create your own board based on this. As well as we will try to release all the software that we are currently creating. So that also means we will try to fully upstream the S32K3 support to mainline nuttx. As for the future, we would also like at some point to port PX4 Autopilot, which runs on top of nuttx to this board. And perhaps if there is still some time in between at some point, we will try to create more example software so that it's easier to actually start developing on this board. And we also have perhaps some new hardware planned in the future to actual spin-offs of this board for specific applications, because this is a very nice development platform. It's already quite small, but yeah, it's probably not optimized for all applications that we might envision with this chip. So at some point there will be other spin-offs. So that's the main reason why we are currently working on nuttx support for S32K3. And Peter will now take over to discuss the actual chip and its features and how we are porting everything to nuttx.
Yes, one moment. I think you're still sharing.
Yeah, I'm trying to stop it.
You guys seeing my screen now?
I see myself coming from your screen.
Okay, and then you're seeing my screen. I think something, yes. Okay, so...
You're in yeah, now you're right. Okay.
Yes, okay. Let me just give me a brief introduction to the S32K SoC family. It's pretty much just like a general purpose MCU, but it's made for automotive the industry, and it's has a lot of functional safety features. And in the automotive industry, they have this automotive safety integrity level, and the highest right now would be ASIL D. And this is what the K3 compared to the K1 has improved on. And there we have lots of features that can help with us with that. And I think the biggest example is having the lockstep core available for your system. There are also different variants with dual cores and even triple cores. Our presentation is focusing now on the K344, which is the dual core lockstep M7 system. And it pretty much has the typical general purpose peripherals. It has the 100 megabit Ethernet, so that's where we also use the two-way Ethernet, and it has a lots of CAN compared to other microcontrollers. Yes, so porting nuttx to the S32K3. Like Jari showed, we're still developing this small board, and there's also a reason why we're developing such a small board, because typically these evaluation boards tend to be very big, which is nice for debugging and developing. You can probe everywhere, but of course you want to have a small one. But right now we're working on this big board, but there's built-in debuggers, and we have lots of probe points for that. So what were the first steps to get started, to get your complete new SoC ported to your nuttx? So first we just started to look at the reference guide regarding to porting. It's quite helpful. Fortunately, it's mostly focused on boards, but if you look at existing architectures, it's fairly simple. And we're also lucky that the K1 is K3 is a continuation of that, so we could reuse some ideas there. But primarily, it's just defining a complete new architecture, selecting the core you already have, and nuttx nicely uses the general purpose registers from the Cortex M7 core in our case. And you get already lots of features in there. And pretty much what you would have to do then is creating a start entry point in your SoC folder, and pretty much think about the basic initialization you have to do for your microcontroller. So starting by clearing the RAM, setting up the clock, and creating a very basic PIMX driver. So for us, kind of was the question is where to get started. So our goal initially was to figure out, okay, how can we get a very simple UART driver going and get just the nuttx debug print statements out. And if it crashes, we get a nice stacked up see what's going wrong. And this was straightforward to get quickly started. And we were eventually quite surprised how things went. And I think when we had the full UART driver up and running, we pretty much already had the nuttx shell running. Although I gotta say we had some challenges during porting. So there's always, I would say every SoC has its own nice boot procedure. And I think for us is that we really have to double check if the vector tables are correct. So if you misconfigure that, you can get in weird states and weird calls. Also, we had this nice debug board, and if you have a clock out pin available, it's really advised to make that to be able to probe that and just double check if the clocking is correct. And also in our SoC, we have a boot header, but there are also different security or safety features sometimes in MCU, and it's good to double check that so that you don't accidentally break your MCU, which is the worst case could happen. But in our case, since we have a multi-core MCU, what you see is that these boot behavior differs. In our case, we had to provide a starting address and also provide the correct address for the vector tables, which was the problem we were mostly facing. So pretty much when you're done with the initial architecture, you also have to create a board definition to really get a nuttx up and running. So then again, you can still go to the nuttx official porting guide, and there it's quite straightforward to get everything going. Also, the linker script, that's also in your board file. So this is one thing you really want to double check and also correctly configure. My advice would be that if you have an SDK from your board, usually they come with an example project, and try to use that linker script as a reference, and then try to expand it to the reference menu of your board. Again, it's about the boot header flash protection. And pretty much if you have that running, you can pretty much just compile nuttx and get your shell up and running, and then it's just a matter of adding all your extra drivers. So we are using nuttx a lot for our projects to get easy software development. But if you look at it, it's like how easy it can be to just port such an operating system to a new MCU. I was kind of surprised that, of course, getting advanced drivers to work is a bit of a hassle. But if you take this initial step to get everything to work, you suddenly have a huge ecosystem working on your new chip. So status report right now, we got it successfully running on this big evaluation board. So next step would be also converting to the Canop board Yari shell, which is mostly a matter of changing the pin boxes and the clocking crystal and so on. And we hope to release the K3 software port to the public around Q1 2022. Current state is that we have the UART driver working, pin mixing, GPO, I2C. And right now we are working to get SPI, CAN Ethernet to work. Also, we have two special drivers here, which is the Watchdog shell, which also uses the FS26 chip, and the fault collection unit. I'll get there in the functional safety. So in our project, we are looking at mobile robotic solutions, but we're also looking at functional safety solutions for these autonomous vehicles. And what we're looking at is that we try to reuse a reference platform. So in our case, the Canop K3, if we want to use it with a VMU, whereas this Canop, we want to incorporate it with the PX4 autopilot ecosystem, but then we also want to provide a nice basis that you might be able to certify it up to these high integrity levels. Fortunately, if you look at real certification, software certification is very complex, can also be very expensive. But since we have these hardware features from our automotive processor, we want to enable them and showcase already the power of these solutions, and also ensure that at least the hardware has this high reliability, and then the software would be the next step. So I think the primary features we now have in the K3 would be a lockstep MC core. We have on a lot of places ECC memory, so on RAM, on caches, on the DMA buffers of the CAN driver, for instance. So there are like look-ahead buffers that also use ECC. And we also have this special fault collection and control unit in the K3. And right now we want to see if we can also integrate this into nuttx to make that easy to use and configure the watchdog or configure the handlers of this hardware monitoring unit. And if people have, for instance, a drone, a PX4 autopilot, and there is these hardware faults occurring, you can get to a stable state. So our goal right now is to make these drivers and showcase that. Also, another one is so the S3 to K3 family chip we have also is combined with a I would say smart functional safety SBC, so power supply DC converter. And what the FS26 can do is that it's connected to what's it called again? It's connected to FC0 and FCB pins directly to the MCU. And if there is a fault occurring, or you have these on-demand built-in self-test of hardware and it fails, the power supply can even reset the MCU. So this is really about high integrity. And these things are very nice, and sometimes they're complex to set up. But I think if you can combine this and have a high-level solution, and nuttx, we have a nice demonstration, and we make this these automotive technologies also accessible for everyone. And then, so in our case, it's mobile robotics, it's industrial. But it's pretty much everyone that wants to make a nuttx application, but wants to really think about functional safety. You can use this solution for that. Conclusion. I would say, nuttx, it's a very flexible platform, and for our business line and where we're working on, we really like to play around with it. We really like if we have new people and are comfortable with POSIX, they get easily into the system, and people in background with just embedded systems, it's fairly easy to make nuttx compatible drivers. And actually, we are thinking about.
This is a little quote from one interview on EE Times that Tio Suyan, our CEO, gave regarding his feeling on Expressive and regarding his feeling on open source. And this is a little bit another quote. This one is on our website.
Yes, I can see it here.
Okay, now, okay, good. So, as I was saying, we decided that the company decided that it should be contributing more to open source projects, not side contributing, and of providing code that people can look into, but also forward those changes to the main projects. So in April 2020, a little bit more than a year ago, the company started third-party frameworks or third-party platforms team. Currently, we work with nuttx, Zephyr, and Msu Boot. Of course, we do have some other ideas, but they are still too preliminary to. Location for this team is mostly in Campinas, but as would be expected, we do collaborate with several people within the company on the main offices, which is. We do also have a few remotes that are currently on a full remote position, or eventually we will relocate to one of our offices. So this team is a little bit different from the current work on ESP-IDF, as our goal was to contribute and forward this contribution to the main project. This is important because it sets a lot of strategies that we have adopted for the supporting of our devices. Also important to note during this presentation that although Expressive has either announced officially or someone has found through some obscure commit on our GitHub a new device, but currently available for purchasing to put into products and to build systems with, we have ESP32, ESP32S2, and ESP32C3. So everything that we're going to talk is going to be on top of those devices. And like I said in a few posts around, there will be spoilers on our general, more general strategy for what's coming. So just as also a general, how can I say that, a general strategy, how we would approach our devices. Of course, the first things should come first. We have to support the CPU to have it running, to see some shell on it. For that sense, there are a few peripherals that are mandatory. Without the CPU, there is nothing. So it's quite obvious that this one would be the first thing to look into. Second, it's a Wi-Fi MCU after all. If we don't do Wi-Fi on our MCUs, it's going to be just look like a regular MCU. So Wi-Fi and Bluetooth when available. Second things to support. And after that, some basic peripherals. If we look into a device that has a GPIO and some Wi-Fi, we already have something for IoT. You can control the light bulb and you can do some very basic IoT applications. So this is the order we have adopted. Of course, after that comes SPI, I2C, and all other peripherals. Some of them, due to ESP32 architecture, they are mandatory. But some of them, we can just do them later as we progress with the port. And just like I said, this team is different. It's not our goal to fork projects. The idea is that we contribute directly to the community. To do that, we have to comply to standards and community rules, and also to help this community to thrive, and eventually hope that our contribution will allow the community to grow. So that said, let's dive into the support itself. So this is a small list of the what we think it's the more important features on ESP32. It's a full-featured device. It has a lot more than this. But on what we think it's important, this is our current status. Some points to note on this list is Wi-Fi. Since Wi-Fi is really important to us, it's work in progress for forever. So we will always be doing something Wi-Fi related. So even when we are done, there's always a way to make it faster, reduce memory footprints and stuff like that. Second, there's some features on ESP32 that we think are really important for the IoT space, which is the low power and especially the dynamic frequency scaling, which we're thinking and seeing how we can support that. And also to notice, we have the ULP, the ultra low power processor, coprocessor. It's already it's supported through IDF, but not supported on the regular project flow on nuttx. So this is another thing we're thinking how we're going to add support for that. So as you can see, it's a pretty decent support. It's pretty sufficient for most of IoT applications. And there are some peripherals here we are still on planning stage to support them. The ESP32S2, on the other hand, our support has just started about 1 month, I think, something like that. So it's quite recent. We already have the CPU supported, and most of our peripherals are not supported here yet. One important point to notice here, ESP32S2 does not feature Bluetooth, but it features USB on the go. So most importantly, I think for these devices, USB on the go currently released is the only device that we have that has USB on the go capacity. It's most likely that we're going for Wi-Fi, and right after Wi-Fi, the USB on this device. And also the ULP here, it was our first RISC-V device. People don't know it, but the ULP for ESP32S2 is a RISC-V core. So yeah, once again, we have to figure a way to support it on the project flow. For the ESP32C3, which most people think of it as a replacement for ESP8266, also the support is quite broad. Also to notice, it doesn't feature an Ethernet MAC, and it also doesn't feature an USB. The USB that it has, it's more of a console. It's a USB to serial in chip, so it's not a USB that you can quite use for very general purposes. And it also features a ULP that we also have to handle. So this is the scenario for a little bit more advanced than the ESP32S2, but not as complete as the ESP32, regular ESP32. So Then this is our current picture. This is what we have been working on. This is what we currently have been doing. So what's next on development? What we're thinking and what we are doing currently. So this is where the spoiler starts to come in. So our current efforts is regarding getting ESP32S2 to the same level, at least almost the same level of support as ESP32 and ESP32C3. And also we think it's really important to add some boot and update features. As we know, IoT applications are plagued by the lack of updates, the lack of secure updates, safe updates. We feel that every platform we put ourselves into, we must have this feature before we can say it is in production status. Also not only for security, but also I don't like that feeling that when I'm updating my device, if I have a power shortage and it's not battery backed, I'm going to have just a brick. So the idea is that not only we should have secure boot, flash encryption, all that security features, but also safety features like can my device resume its update if something bad happens, if something goes wrong? Can it be back come back alive? So this is, we think that's important, and that this is actually what we call image safety and image recovery. And secure update is, I don't want some hacker in the middle of my communication to the cloud, getting into and sneaking a firmware, replacing my my standard firmware or my application. So I don't want to run these risks. So this puts us into this list of general activities. So we are starting to work on flash encryption. ESP32 is architecture is a little bit different. All of its flash memory it's not in die, it's an external chip that does it. So we do have a flash communication through SPI that could be sneaked upon to prevent that there is flash encryption. That it's as we use the term layer 2 cryptography because it happens on the layer 2. If we think on OSI OSI layers, we're planning secure boot. We also, of course, are working on ESP32S2 peripherals. And one thing that I put it first, but I let it for the last, but not least, is something that I'm really proud that we have been doing, is porting Msu Boot and having Msu Boot to work with nuttx. For those who are not aware of this project, it comes with a lot of those features that I've just mentioned regarding image safety, image backup, and things like that. It also comes with a full set of APIs that on Msu Boot point of view is what it calls application. To understand a little bit of this, we can say that the host OS is going to use to access all the functionality that Msu Boot offers. So it's a pretty interesting project that we started to contribute, and we are porting to nuttx. We already have some experiments. We also already have published on Embarcados, a Brazilian website of technical content, a tutorial on how to build Msu Boot. And also on that tutorial, we offer a precompiled image of nuttx, proving it can work with Msu Boot. And of course, our goal is to bring that to all our devices. Now, diving a little bit into ESP32S2, what we have planned is what is marked on blue. So like I said, Wi-Fi is really important, USB is also really important, and of course, all other peripherals, they're important, but we think that these two, since they are the biggest differentiators for this device, is the Wi-Fi and USB, so they have to come first. And of course, all the rest of the peripherals for a full IoT experience, as to say. Regarding Msu Boot, we have some PRs in place for ESP32 and ESP32S2. But by the time I did this presentation, they were pending. ESP32C3 is Msu Boot port is in development. It's understood the Msu Boot port itself, so it's on development. After the Msu Boot port is ready, then we get to make it work with nuttx. And like I said, besides that article on how to use it, we don't plan to stop there, because we think it's something new, something we devoted a lot of time and effort to understand how to make it work. So it's more than important and obvious, even on our point of view, to share that knowledge through some tutorials, some articles, sometimes on Embarcado's website, sometimes on Expressive Medium, wikis and stuff like that, to share what we have learned and how to make Msu Boot work with nuttx. As happened recently, an update, our PR, when I kept things just to show that things are moving, and they're not moving slowly, they are moving on a very decent pace. Our PR for ESP32 was approved. Now we have the second part of this work, which is make the nuttx side of the tasks. And then we can say that we have Msu Boot properly working on nuttx. Currently, we have not on production state. It's quite it's on what I used to say, it's on hacker level for users. Of course, we want to make it more on a more better user experience, but it starts with our PRs getting accepted, and we just head for the ESP32. Now the rest of the family comes one after the other. So that said, for what we have, what we are currently doing, what we will be doing, and what's the future of this project within Expressive. Well, I get this question all the time. Every time I talk to people, they start asking me, Ricardo, is Expressive going to keep supporting newer devices? Is this something that we're just doing for the current ones and then we are moving to another project? Well, I like to say that first, I like to start that because people start to see things being supported on ESP-IDF. I said, well, why aren't you starting on support for other stuff? I said, well, our support actually starts with ESP-IDF. So every operating system that we currently use, our support starts with the ESP-IDF because it's the tool we use to test the chips, to evaluate them, to see if they're working properly. So our support starts there. Also, we enjoy the work of our other Expressifers, so we can just take the code they created and we can get inspired by it and do our porting. So our support starts with ESP-IDF. It's part of the process. And second, what I replied to that question is, well, we created a team, the third-party platforms team for that. So yeah, most likely we're going to stay. So yes, we're going to keep supporting your devices. So just also to take that out of our to take that from the front of us. Yes, we plan to support ESP32S3, we plan to support C6, we plan to support the recently discovered H2. So support is going to start. I would expect that support for those chips, once you see them supported and released on IDF, then our job starts. In the meantime, if you might think what we will be doing, well, that's what I'm going to talk next. So while we wait for these devices, there is still a lot of stuff that we have to do for the currently released ones. So talking about that, then we start talking about our future goals. So yes, we just to reinforce the message and set it on a single sentence, it's our plan to keep supporting ESP32 family device, not only ESP32 regular and those currently on the market, but the future that are to come, and those that were not announced yet. But as you can and you might imagine, our R&D is working on. Second to that, we want to get these, not only, it's not something we want people just to try and say, oh, nice, that's cool. That's not the idea. The idea is that people actually put that into products. So for that sense, reliability for our devices is a must. So how we're going to approach that? Whenever we find something that's a bug, or we find some opportunity window to improve something, we go and do that. So we go for ESP32, and eventually we can move to C3, then to S2, and eventually when we have it as C6. So working on the reliability of our devices is going to be part of our goals always. So the idea is not to just let a bug sitting there like forever. The moment we figure that and we understand how to fix it, it's our goal to go and fix it. And finally, it's important for us to keep collaborating to the community. So now that's more on long-term strategies. Now a little bit more on what we are currently planning, and on planning stage that we thinking to start the work as soon as we finish what we're currently doing. Is there is some Wi-Fi drivers improvements that we are still pending to deliver to ESP32. Also support a few protocols that we are currently not supporting yet. So yes, Wi-Fi is going to be something we will. Like I said, I don't think we are going ever to stop working on Wi-Fi. But this is, I think it's one of. It's not going to be a fine tune. It's going to be a major update that we are planning. Also, this idea of dynamic frequency scaling, it's important for our devices. It lowers the power consumption by a lot, so it's important for battery-powered applications. Also, CAN bus, it's something that people we're seeing some movement and some people in the community asking for that. SDIO, SD card, really important for data logging and stuff like that. So yes, it's something we plan to work on our next feature loop, let's say. And also again, it's currently someone can just do something on IDF and then take that and try to those ULP binaries and put to work on nuttx. But we feel that okay, it's doable, but it's not the better way to do it. So yes, a proper ULP support is something we have to figure how to work with that. As asymmetric, we can consider this as more of an asymmetric multiprocessing of sorts. So how to handle that. And finally, there is Msu Boot. We enjoy joining this project. We think that it adds a lot in terms of features. Having it to work with nuttx, we already have some push requests regarding the nuttx port itself, not only the expressive ports, but the nuttx port itself on the Msu Boot. As far as an important thing also, as far as I know, we are the first ones to be doing that, to have that working. I can be wrong, but so far from what we have researched, only ESP32 is working with Msu Boot and nuttx together. So we do plan to keep contributing, we do plan to keep improving, and also we understand that we open the path for other players in the nuttx space, in the community, to start adding the airport as well. They can take a look on what we did. Of course, they can improve it, and we would be glad that they do. So, but we think it's nice that we kind of open that door for everyone. And as such, we don't plan to stop it. We have dedicated people working on Msu Boot, and we also have part of our nuttx team working on this integration. So it's a work in progress, and of course, there is always a lot of room to improve.